Good? Yeah, okay. Yeah, about the ice cubes for whiskey. So we've got some ice from Bingo World from 3 years ago in our cold room in the freezer. And I'm thinking like we need to have a cocktail party with Bingo World ice that's been aged a few years. Those might be some expensive cocktails, so let's see. Fundraising event. Anyways, yeah, so again, I'm Kevin Hammonds. I'm assistant professor in civil engineering department at MSU, also the director of the Sub-Zero Research Laboratory, a multidisciplinary space, mostly built up by Ed Adams, wherever Ed went. Yeah, so kudos to Ed for kind of getting the Sub-Zero to where it is today, and people like me get to come in and take advantage of it with my students. All the resources that we have here, multiple walk-in cold rooms, lots of instrumentation. We can basically simulate nature indoors in a controlled environment about as good as you can do anywhere in the world, frankly. So we're able to do a lot. We're able to learn a lot about processes that happen in the snowpack that you can't really do outside because you can't control all the variables. That's sort of our thing. Today's talk is going to be kind of highlighting some of the work that we've done over the last few years, maybe even 4 years in the lab that haven't really had the opportunity to share locally because we haven't had this event in so long. So I've given a couple talks here and there over the last few years, but not really on this material in particular. I've got my acknowledgments at the end, but I'd like to acknowledge that all the work I'll be showing today is mostly been done by my graduate students, PhD student Kristani, who recently graduated. Evan and Jamie are here in the audience. Let's go ahead and give them a round of applause, guys. Yeah, come on. They're doing all the heavy lifting, and they can correct any of my errors throughout this talk. Which is going to be about what we've been doing in the lab as it would pertain to addressing liquid water flow in snow with hyperspectral imaging and radar primarily are the two tools I'll be talking about today. And I'm going to propose to you that we could be on the cusp, or are on the cusp, or actually have been for a while, a new era in snow pit characterization and potentially also mapping over larger areas. So to get started, I finally learned from some of the others in the room, like Carl, for instance, who always got to show an avalanche video right off the top, right? So many of you probably remember this avalanche cycle from Bridger Bowl back several years ago. It was a huge wet avalanche cycle. This is sped up a little bit, just so you know, but part of this talk is going to address what we could do about wet slab avalanches. As you guys all know, they're a cohesive layer of snow that releases once you get water to percolate down onto a weak layer, maybe down onto the ground. Whole large starting zones can pull out, can trigger other things off on the side, can lead to really large, destructive, big avalanches in terms of their size, their duration, their run out distance, things like that. So something that's generally of everyone's concern, I would imagine, for the ski patrol avalanche folks in the room. This is probably what you're thinking about right about now, because isn't it supposed to be like 60 degrees like next week, this weekend, something like that? Yeah, right. I don't know. Well, we're still living on the ice cap here in Bozeman, but it's getting ready to get warm, and things are probably going to change and happen. Did you guys see those trees get knocked over? Yeah, super cool. I love this video. This video is sped up, and I've shortened it to 1 minute, but this thing flows. It goes on for like 9 minutes, like the whole video, just the flow of the debris down this gully up at Bridger Bowl. So just a good illustration of what can come from wet slab avalanches, and kind of what you have to be thinking about and trying to forecast those as a forecaster. So along those lines, I don't think I have to, I don't know, this probably isn't a surprise to anyone in the room, but I think avalanche forecasting is hard. I think it's probably one of the hardest jobs out there, actually. And part of that is because you have, at the forecast centers or even at the ski areas, you have pretty limited resources to address large areas of terrain that you're responsible for, and you're trying to give an accurate forecast for. And so I feel like there's always this question of, we can learn a lot from digging snow pits. Clearly, we do our stability tests, we characterize the snow pit walls and things. But it doesn't make sense to try and do lots of those everywhere because you spread yourself too thin. So the question is it better to cover more ground, to just go see more about what's going on out in the terrain that you're forecasting for? Or is it better to really thoroughly dig more pits and spend more time in them and learn as much about what's going on with the microstructure in the snow as possible? I think it's one of those questions that, it's a balance, right? When you're in the pit, you can spend a lot of time there, obviously. You're recording all these different things: depth, hardness, grain type, grain size, temperature, density. trying to estimate things like liquid water content, liquid water location. You're doing all your stability tests down here, so you could spend a long time in these pits. And so part of this talk, the new era in snow pit characterization is, can we make this part of the job a little bit more efficient? So I guess the future is here from the standpoint, and depending on who you ask, would say it's actually been here for a while. We're just starting to recently take advantage of some of the modern technology and equipment and applying it to snowpacks, applying it to avalanche forecasting in particular. So in my group, we've done quite a bit of work on LiDAR. Jamie's done a lot of work on LiDAR. Chris Donahue, who recently graduated, was working on this upward-looking radar project and also doing hyperspectral imaging. Basically, everyone in the group now is doing hyperspectral imaging. The focus of this talk isn't going to be, I've given talks on this in the past, happy to answer any questions about it, but we're mostly going to be looking at how we can use upward-looking radar to monitor the location of liquid water percolation in snow and to retrieve snow depth, and then hyperspectral imaging to retrieve things like liquid water content and the specific surface area, that maybe the surface density, to map surface ore, to do a lot of different things. If you guys haven't heard of upward-looking radar before, kind of the idea behind it is that you put a radar under the snowpack looking up. And so as liquid water builds up on the surface and starts to percolate down, that signal doesn't get attenuated like it would from the top. So you're actually able to look up and see the water flow. You can kind of see where it is in the vertical height at any point along its flow path down. I think the Swiss might have been the first ones to do that I know of, like in 2013, so quite a while ago, but it hasn't really taken off, hasn't really been applied. Certainly not applied in the laboratory that we know of. So those are the two technologies I'm going to focus the talk on. Next, I want to introduce this concept of specific surface area. That's something that in the snow science world you hear thrown around all the time. Really important parameter that characterizes things about the snow morphology, in terms of the geometry of the ice grains. It also directly controls the optical properties of snow grains, so that for any remote sensing application, it's hugely important. And it's also, which means it's also a controlling parameter on the albedo of snow, which for climate science is hugely important. So specific surface area is this metric that we can apply to snow. You can actually apply it to any object. It doesn't even matter, because what it is just a surface area, most simply put, a surface area to volume ratio of the object. And so I have two different examples here from micro CT images taken in the lab of surface ore on the left and some old snow on the right. So if you think about these as like cornflakes, and you think about these as like Rice Krispies, like these are going to have a higher surface area to volume ratio, so they have a higher SSA. Whereas the rounded grains, the old rounded grains, have a lower surface volume, or lower surface area to volume ratio, so they have a lower SSA. And so we're kind of going with this is like, it's not only important to the remote sensing, the retrievals of these different properties of the snow grain, but it could also be, and to some degree is correlated to the morphology. The morphology is like literally what you're trying to characterize in your snow pit wall when you're looking at grain size, grain type, things like that. It's wrapped up in this parameter actually. And so how can we use that? Maybe to our advantage, I guess, is the question. So I pulled up a plot from a paper which I admittedly kind of cherry picked. It's not always this clean. But anyways, where you can differentiate between different particle types based on specific surface area. Like you have your decomposing precipitation particles here, your rounded particles basically here. You've got some faceted crystals and some depth hoar crystals here with specific surface areas that just correlate nicely to the grain type. And so it kind of suggests, well, what if we started looking at the snowpack not in terms of snow grain type and grain size, but specific surface area, something that we're not really going to argue about. It's an objective measurement, right? Like it is what it is. It's a number. And what if we plotted like a whole mountainside, basically. This is up at the Yellowstone Club from some of Jamie's data, the data they collected with LiDAR, where the new snow, the new freshly dendritic snow on the surface has a high SSA versus the old snow, this is like after it hadn't snowed in a long time, has a low SSA. And if you just kind of plot that on a grayscale, you can see the difference quite clearly. So what if we were able to start doing this, routinely over large areas or small areas to characterize what's on the surface, but not just looking at what's on the surface, we could also apply this at the smaller scale to the snow pit, if we have the right instruments to do these retrievals for a specific surface area. There's also recently put out some new point measurement SSA devices, I think from the SLF, that aren't that expensive, to where you could take point measurements over the snow depth of your snow pit as well. I think those are like maybe $1,000 or something right now from the SLF, and I'd like to get one. I don't have one yet. Okay, so that's some background, in terms of what SSA is and how we're gonna apply it. And now I want to take you through what some of our experiments were, and then to our results. So in a good portion of Chris Donahue, who graduated with his PhD last year, a good portion of his work was spent looking at the applications of upward-looking radar to track liquid water flow through snow, trying to figure out things about percolation behavior, timing, things like that, how we could correlate that to a radar signal. So the way we did this in the lab was we built a box that's an anechoic chamber, actually, so it has this radar absorbing foam around the inside of it. We put our block of snow in there. We have our radar down below looking up, and then above we have these simulated solar lamps that give like the full spectrum and intensity of the sun. So we can melt the snow from the top, even though we're keeping the room below freezing, right? So just the solar input that's causing the melting. This is a video of what that looks like, where in this particular experiment, we had a little black dye tracer. So you'll see a little black layer show up that percolates down, and we image that later. But anyways, this is just what a typical experiment looks like. And here's what some of the data looks like. So top of the snowpack, bottom of the snowpack, we get a large radar reflectivity once the water starts to pool at the top. And then at some point, it starts to percolate down. We lose that signal in the copole for any of the radar aficionados in the crowd. And then when it starts to pull at the bottom again, we see that big signal again. So we can get the time, from this, we can get the time that it took. We also were draining the box on this experiment. So we've got, the water mass flux moving out of the box at any point in time. So you see how that ramps up, like as the water starts to pool at the bottom. This was kind of one of the early experiments that we did. We've done a lot of them since then, including not perturbing, but creating different types of layers in the snowpack that you might see in the real world, like creating capillary barriers, like mid-pack, where you have small grains over coarse grains. So again, we get the melting at the surface, it percolates down, it pools again at the capillary barrier. Percolates down again and then pools at the bottom. And capillary barrier, I think, is a neat example of how this happens, because that's not something, when you're just looking at a snow pit face, that's that easy to really identify. We can see surface hoar layers, we can see ice crust, we can see all these different kinds of layers, but just the change in grain size, which can be subtle, can cause things like capillary barriers to form, and you can get liquid water pooling at those interfaces. And so, interesting case study. Notably, a lot more to do on that in terms of being able to apply that to avalanche forecasting. So this is
there when you change grain size to create a capillary barrier, is there changing from a large grain to a small grain, or a small grain to a large grain, or does it matter? Is it just the change that creates the capillary barrier?
It's small grains over coarse grains. Okay. Yeah, is what you're looking for. That's right? Yeah, okay. In general, yeah. I've got some people planted in the audience to give me like, yeah, you're on it. Got 2 little kids at home. I don't sleep very much, so I'll take all the help that I can get up here. Yeah, so that, to answer your question, yeah. And there's been studies on this in the past. Like, there's a lot of literature out there on that interface capillary barriers, but it hasn't been applied to like avalanches, the mechanics, what happens when that water pools up. All right, so that's upward looking radar. Let's move on to hyperspectral imaging. Who knows what a hyperspectral imager is or what it does? I mean, I know there's at least a few people here, right? But they're the ones I planted in the audience, but that's okay. Before we started this work, I didn't know what it was either. I was like, I don't know what a hyperspectral imager is, but I gave a talk at the Ellen like 5 years ago now or something. And this guy came up to me after the talk and was like, I work for this company in town called Resonon. We make hyperspectral imagers, and it'd be really cool if we pointed them at snow in your lab. And I was like, yeah, that would be really cool. Let's try that. That led to a PhD, for a student, honestly. And we've just been borrowing more or less their instruments. I think we're just now able to buy one. But we've just been borrowing their instruments the whole time. So what does a hyperspectral imager do? I think the easiest way to think about it is to think about like your cell phone camera, any digital camera you have experience with it. The image that you see is a combination of red, green, and blue, RGB, in some different combination, makes all the different colors that you have in your image. A hyperspectral camera operates just like that, except instead of red, green, blue, pretend you broke that into a spectrum of like 1,000 different bands. And it was like that 1,000 different bands that make up each individual pixel of that frame. That's what the hyperspectral imager does. And so you don't just get RGB, you get the whole spectrum. And this is just kind of highlighting the optical wavelengths, the ones we can see in color. But this goes on out into the infrared, the near infrared, where you can't, which are non-optical wavelengths anymore. So this is the kind of data you get. And so at each pixel in an image, you've got a whole line, this whole curve of data to work with. So it creates an extremely rich data set if you know what to do with it, which is what we were working on and other people have worked on in the past too. But just to give you some examples of how it can be applied is that you get different spectral curves for different types of materials. So for instance, water is very absorptive. It doesn't have much reflectance, relatively flat. The sand here has kind of its own characteristic brown curve. The trees, own characteristic green curve. And then the snow, its own characteristic blue curve. And as it turns out, for ice and snow, if you're looking at it, the reflectance over these wavelengths, the curve always looks like this. And these little peaks and valleys are almost always in the exact same spot. Magnitude can shift up and down, depending on things like grain size, specific surface area, things like that. But in general, you get the shape. And so what we started, and others have started to do as well, is start to utilize some of these different points, some of these different bands to pull out information, to like pull out some characteristic properties of the medium that we're looking at, which for us in this case is snow. So that's what basically a hyperspectral imager is. This is what the unit looks like that we're using. This thing costs right now probably like 30,000 bucks. They're getting cheaper, they're getting lighter, they're getting flown around on aircraft and on drones. I think it's really just a matter of time before this is like a pull out of your pocket instrument kind of thing to be able to use. The data processing isn't terribly involved. So I think it's definitely on its way. And I think the work that Chris and the group have done has been outstanding in terms of moving it forward for applications to snow. So now, who knows what a hyperspectral imager is? Everyone, we're all experts now, right? That's all you need to go use it, basically. So what did we do with the hyperspectral imaging and the upward-looking radar? Here's some more examples of applying the hyperspectral imaging to some experiments in the lab, where again we're melting our snowpacks in the lab. So this is just an overlay of what the camera sees. So this is like what the liquid water percolation looked like if you just cut the cross section out. Chris took this up to Bridgeable, applied this in the field. So he's shading the top because he wants like uniform reflection. He's got his halogen lights on here, and this is what the camera sees in terms of after our retrieval has been applied to it, which was really the bulk of his dissertation, was developing these retrievals that are very statistically robust to be able to retrieve over the entire snow pit wall. So this is the specific surface area at any point and the liquid water content in terms of its percent at any point, color shaded here. Just take a second to think about the step forward, which I feel like was a huge leap forward in what we can do for characterizing the snow pit wall. Instead of having like these point measurements, just down the ruler on the wall, this is pixel by pixel by pixel by pixel data all the way across. That's giving you some pretty, what could be useful parameters like SSA and liquid water content when it comes to looking at where the water is in your snowpack and how saturated is it? You know, you can see quite clearly. This was I should have mentioned this is in the spring when they were having a melt event. So you can kind of see where you've got a lot of liquid water near the top. Some of it's percolated down. It started to pool in different places. You can see these. I mean, even without thinking about what liquid water content SSA is, just look at the definition you get for all the layers, right? Like it's really hard to just see that when you're looking at a snow pit wall. So that alone, I think, could have its own benefit in just identifying where you have the different stratigraphic layers in the snowpack. So Chris took this one more step, and we wanted to learn about percolation in snow. How does water actually move through the snowpack? And so what he did was a serial sectioning experiment where he took his block of snow and he would cut off a 1 centimeter slab and image it, cut off a 1 centimeter slab, image it, rinse and repeat until there's no more snow. And then he pulled that all together into a 3-dimensional image, basically, which is what's shown over here. So this is being shown in terms of liquid water content, where it's going from opaque to transparent based on being very low liquid water contents to very high liquid water contents, where you have the highest liquid water contents, where you have all these little drainage channels that form. So this is showing preferential flow, basically these preferential flow paths that develop. So even though the whole snowpack is like semi-saturated, it's concentrated in these flow paths, and we're able to see those, measure those, quantify those with these kinds of experiments. I'm afraid to call on you, but yes.
No, I have a question. The experimental conditions. So when you did the cutting, was the melt were dyes or not?
No, it was not. Yeah, so no dye used. That's the advantage of having the hyperspectral imager, is that the retrieval can tell you where the water is, even if you can't see it. There's no dye in the snow. So this is just from the retrieved data. Thanks for an easy question, Corinne. So it's pretty cool. It's kind of a tangential thing that we're looking at is liquid water percolation snow. It's not like really mechanics focused, but the application, I'll come back to this later, I think is huge for what we can do with this. I'm going to go off on another little tangent, and I'm really tempted to bring Jamie up here for this, but I'll do my best. Jamie has come up with a classification method where he's been applying the hyperspectral imager to classify presence of surface hoar on a surface. So imagine being able to like fly your hyperspectral imager around your forecast area and just get a map back. I've got surface hoar here, I don't have any here. We just had a wind event. Where did it get destroyed? Where did it not? Fly around again. I've got surface hoar here, I don't have surface hoar here. So you don't have to go out into the field and dig a bunch of holes to figure that out. And so the way he did it was using basically a metric of the surface roughness of that surface hoar creates compared to other grain types. So what I've highlighted here is how distinct the difference is in his calculations, his retrievals here. These are, I'm not going to try and tell you what these are, but anyways, like you can see the difference here. Like it's obvious that this is surface hoar. This is like a bunch of different kinds of grain types that you might see at the surface, and the surface hoar really stands out. He did a side-by-side comparison here between surface hoar and rounded grains with the hyperspectral imager, ran it through this classification algorithm that he developed, and gets like 84% accuracy on mapping where the surface hoar is, which is pretty darn good. If you see a bunch of patches like this around on your map, well, it's pretty confident that's going to be surface hoar in those areas, whereas where there's no surface hoar, there's like nothing there. So it's a really cool application for the hyperspectral imager that kind of takes us even beyond what we can do, what I've been talking about so far with liquid water flow and preferential flow paths and things like that. So this is work that's ongoing that I hope Jamie will be, ready to share in the relatively near future. It's similar venue like ISSW or something like that. Okay, so now what do we do with all this? Kind of coming to the end here, forecasting applications. So I picture this, new era of snow pit characterization and surface mapping being applied in a couple different ways in the near future. One, can we make the time we spend in our snow pits more efficient? And I think the answer is yes. If we can, start applying hyperspectral imaging, we could start looking at our snow pit like this instead of, like this. But there are some things we're not ever going to be able to get around, like snow depth, unless you have like a radar or something. You're going to have to measure the hardness manually. You're going to be measuring temperature. You're going to be measuring. But if we can start replacing the idea of like grain type and grain size morphologies with something like specific surface area, which isn't like a unique idea that I've had. I think the Swiss have probably been pushing this the most out of anyone that I've heard of in recent years. But anyways, it's just the idea of like, what if we just all started using a number instead of like a subjective grain type or grain size? So the hyperspectral camera can give you that. The pit wall density, liquid water content, liquid water location. Still working on the density component, but like the hyperspectral can give you this. You don't have to just like squeeze it and see how much water comes out and, you know, estimate what the water content is. It can tell you. And then your stability tests, unfortunately, still need to be done all manually, which I'm sure you'd all be sad if we came up with some way to automate that too. So as would I. So I think there's a lot of application here for making your snow pits more efficient. You know, again, aiding in the forecasting, and then also for covering more area. You know, if you can get some of these instruments on aircraft, on drones, whatever, you can start to apply it. Or can we get radar, upward looking radar out in the field? Maybe not in every start zone, but maybe at a proxy location close to your start zone or something like that. I think that it's possible to do these things now. It just takes the intent, the investment, the will to make it happen. But if we were able to do this, you know, you could start to get things like snow depth over your entire forecast area from the LiDAR and radar, snow surface density. I still kind of work on that, but I think we can get that from LiDAR and hyperspectral. Surface hoar detection, we can get that from the hyperspectral. Again, if we can get our surface, we can learn something about the surface morphology of the snow from LiDAR and hyperspectral. If we look at it through SSA, we can see where liquid water is pretty clearly with a few different things. Liquid water location in the snowpack. If you have upward radar, you could see where that is. And then we can also map, if you have LiDAR, you could map slope changes in angle and aspect based on snow accumulation and not on like the surface DEM, for instance. You could do that from LiDAR as well. So you can kind of see how the terrain is literally changing over the winter, becoming steeper or less steep, or accumulating snow in certain areas. So all that's possible, I think, now, and excited to see where this all goes in the coming years. Some final thoughts to wrap up on. Recent advances in remote sensing technologies combined with controlled cold laboratory experiments show great promise for being able to, one, more quickly and efficiently characterize snow pit properties. I'm trying to convince everyone that that's true and that that's the direction that we can go in as collectively as a group. We can identify the extent of liquid water content and location in a snow pit. Wouldn't it be great? I mean, I don't know. Maybe I'm just making this stuff up. There's a lot of people who make the call on doing avalanche control at ski areas here today. Would you like to know where the water is, like in terms of depth in your snow pit or in your snowpack in general? Like, just give me a nod, maybe. I don't know. Come talk to me about it later.
But wouldn't you have to still open up a pit wall to see that?
Not with the upward looking radar.
Not with the radar.
Yeah, the radar would it'd be at one spot. So you'd be extrapolating from there, right? But you'd see where it is.
But you could
if you know where that one spot is that's causing problems over the years, that could be helpful.
Yeah. And you'd see whether or not it's pooling. Right.
It sounds like that hyperspectral camera is still quite expensive. A couple like cycles are gonna from you.
Yeah, I don't know. I mean, honestly,
These radar deals. What's the cost?
The radar, the upward-looking radar kit is also from a local company called Sensor Logic, and I think they're selling that kit for like between $2,000 and $5,000, something like that. They've got a whole like downward-looking radar system. This is one that we implemented just for our researchers, an upward-looking radar system, ripe to be developed. And their Sensor Logic guys are definitely like into developing more of their technology and products for snow. Encourage you to reach out to them if you want to learn more about their stuff. And Resonon too for the hyperspectral cameras. Where are hyperspectral cameras in terms of cost beyond the one company I've been working with? I'm not really that well versed in. I recently got a contact from someone in Europe trying to sell me a hyperspectral camera. It looked really slick. It was like pretty small and sleek and said it would do all the same stuff. And I didn't get a quote on it because I felt guilty for talking to them because I've been working so closely with these other guys. But as a matter of fact, I sent them the email. I was like, look, give me a deal, man. Yeah. Hook a brother up. So we can dramatically increase the spatial resolution of snow pit data, making it easier to identify stratigraphic interfaces of interest. perhaps with the specific surface area parameter, and can we expand on the spatial coverage of avalanche forecast zones with these remote measurements, like snow depth, surface density, crystal habit, everything that we can learn. I think this is all possible. I think we just got to like get it out there and need some commitments to technological advance and application on behalf of the users, I guess. Before I wrap up, I want to acknowledge again all the grad students that have worked on this with me: Chris, Evan, James, Christian, who's an undergrad that graduated, Mackenzie Skiles is a researcher at University of Utah that worked with Chris and I on the hyperspectral imaging project. Some of this was funded by NASA, some of this was funded by TARP. Folks at Bridgeable have always been very accommodating, appreciate that. And then Resonon and Sensor Logic are the two companies I've been talking about this whole time in terms of where are we going to get in this, how we've been doing this work. But the last thing that I wanted to wrap up on, because this is like really fresh, this is hot off the presses ideas. There's no work to go along with this, but what should we be doing next in the lab? I'm really excited to have Dr. Kroll here, who's also looking, and she's going to talk next, also looking at liquid water flow in snow, about what can we do to study the effects of this liquid water that now we can quantify and see really well as it accumulates on weak layers in a snowpack. Like, what is that process for like that compaction, the densification of the snow layer, the pooling at the interface, the weakening of those bonds? Like, what is that? What is behind all of that? Can we understand it? Can we predict it? And I got this idea, I got some of this motivation just recently. So this is a picture from my backyard from that last big snowfall we got that shut down Highlight early, which I'm still super bitter about, and upset that certain people didn't make phone calls and get it plowed. But but anyway, so we got like 2 feet of snow in my backyard, and this is what it looked. This is what I like. Walked out in the morning. I was like, "Wow, this is a lot of snow." I'm gonna send a picture of this to my mom. I took this picture. There's 2 feet of snow on the storm table here that I have that I keep on the patio. And I walked out a few hours later. So later that day, you guys might remember, it kind of warmed up. Like, it was in the mid 30s, but still snowing. And this is what that slab of snow looked like on that table. And I was like, there's only one way that can happen, right? Gravitational force. The table is at a little bit of a slope. It's a concrete slab, so don't. So in case you're curious, I measured the angle on this table, and it's like between 1.5 and 2 degrees. All right, and so this is what is going through my mind. It warmed up, whether the water percolated through the top or just it warmed up the glass on the table. I don't know. I don't really care. But clearly, there must have been some liquid water that formed at the interface between this snow slab and the glass plate that apparently made that interface frictionless. A 2-degree slope, and this massive snow is sliding off. How else does that happen? So now think about what's happening in the snowpack out in the mountains where you've got a 30-degree slope and you've got liquid water that's percolated down and saturated a layer. Is it also like becoming frictionless to where it's only held up by the perimeter, like compression, shear, tension of the slab around it? It's not even held by that contact below. I actually want to go back to that video I showed at the very beginning. You guys remember when the avalanche came down and it triggered that slide off to the right? I think that the water was fully saturated, that weak layer in the snowpack. And that slide, when it came by, it took out the bottom support. And without that bottom support, like, there's nothing there, right? Like, the whole slab just came down. And so I'd really like to dig into this, because this really fascinated me, actually, seeing this happen in the backyard on a 2-degree slope. I was actually really psyched, and this will be my last picture. I don't know how we're doing on time, but I was actually really psyched to continue to document this until it like started to calve off like a glacier off to the side. But the two most destructive forces in nature came along and cleaned it off, knocked it off for me. So I wasn't able to continue documenting this. So I'm looking forward to repeating that experiment and
ski patroller.
coming back with more data. So far, they just like to eat the snow and play in it. But anyways, that's all I got for you. Thanks for your attention. Happy to take any questions.
I want to know what Ed thinks of your theory of the water.
I do too.
About the table or the
Yeah, the
kids?
table. What do you think's going on?
Oh, I think that's, I mean, I can't disagree with Kevin on that. Is that what I think there's probably percolation. There's some interface. The friction's not gone, but it's lower.
Right.
Virtually zero. Yeah.
Kevin, two questions for you. One as it relates to the feasibility of a hyperspectral sensor growing on some type of probing device ultimately to not need to cut a pit into the snow.
Yeah, that's a good question. We've actually kind of talked about that just in concept of whether or not we could use this on a probe, on like a telescoping kind of probe. I think it's possible. We could use like a waveguide approach, maybe keep the hyperspectral imager above and just like have mirrors and things, optics basically set up. Possible. We were talking about this yesterday when Ethan gave a talk in my class. We need smart, capable people to spin off new companies from their current jobs and make these things reality, basically, or somehow give us more funding in the academic sector to do the work, which is always a challenge. But yeah.
And my other one for you on upward facing, what's the logistical hurdle right now from putting one of these in a start zone and the whole season as far as getting the data off? What does that kind of look like?
Just the start zone, being in such a kind of remote, isolated place, getting power to it, getting the telecommunications out, challenges that can be overcome for sure, but it's an infrastructural challenge for that. Even just putting this in a flat spot up at Bridger Bowl, we put it up at the Alpine site for a couple seasons. And the first season we dug this big hole and put it in there, and we collected some really good data in the beginning of the melt cycle, but eventually the hole filled up with water and it floated the radar up to the top and just created some problems. So the next year we just put it right on the surface, and anyways, there's some logistical things that still need to be worked out. I think it's really possible. I've actually spent, is Eric Peitsch here today? No, I don't got Peitsch. All right, so I talked with him a little bit because he does so much work with like the wet glide cycles up in Glacier about like, what if you just went out at that time of the year and just excavated a hole under your snowpack and just shoved this thing under there, right, in a Pelican box and just look at the data, see where the water is. It could be as simple as that even. It doesn't have to be, maybe even be a permanent installation, but the capabilities are there.
Yeah. With the hyperspectral, you had like the halogen lights.
Mm-hmm.
Do all of them need those halogen lights? Like in the future, will just in terms of like
Well,
size?
I think they'll just be more streamlined, but you do need to have some control over the illuminating source. So if it's just the sun and it's cloudy or bright or at this angle or that angle, that hasn't been accounted for. I think it probably could be accounted for. It hasn't been accounted for yet in like the retrieval. So it's good to have like uniform illuminations for right now. One more? Yeah.
What's the wavelength of the radar you're using and how far into a snowpack
I believe the one that we were working with was had a choice between 7.3 and 8.5 gigahertz. So it's penetrating the whole snowpack. How deep would it go before it would attenuate?
could you use it for burn?
That's what I mean. We haven't.
You haven't really tested it.
I'm not really sure at what point it would become attenuated just due to the depth, but it'll penetrate any seasonal snowpack that I know of at that frequency.
Thank you, Kevin.
All right, thanks guys. Thanks, Doug.